Did you know that traveling to Mars with current technology takes about 7 months? That's over 200 days spent hurtling through the void of space, confined to a spacecraft with limited resources and even more limited comfort. Now think about this. What if we could shrink that journey in half, or even more? The truth is, the future of space travel isn't just about reaching new destinations. It's about getting there faster, safer, and more efficiently. And that's where the game-changing potential of new propulsion systems comes into play. Traditional methods like chemical rockets have served us well, but they're reaching their limits. As our ambitions grow, whether it's colonizing Mars or venturing to distant stars, we need technologies that can keep up. In this video, we'll dive into the cutting-edge propulsion systems that could redefine space exploration as we know it. From ion drives to nuclear propulsion, and even the mind-bending possibilities of antimatter engines, we're about to explore the innovations that could make interstellar travel a reality. So let's take a closer look at how these technologies are shaping the future of our journey into the cosmos. Picture this: a crewed mission to Mars is underway, and everything seems to be going according to plan until the spacecraft begins to run low on fuel. The team suddenly realizes they might not have enough to make it back to Earth. This isn't just a hypothetical scenario, it's a real risk with the propulsion systems we currently rely on. Chemical rockets, the backbone of space travel for decades, are incredibly powerful for launching payloads out of Earth's gravity, but they're far from ideal for long-distance journeys. They burn through fuel at an astonishing rate, and their inefficiency becomes glaringly obvious when we consider missions beyond the Moon. As humanity sets its sights on Mars, the asteroid belt, or even the outer reaches of our solar system, the limitations of these traditional systems become impossible to ignore. We need propulsion methods that can sustain longer missions, reduce travel time, and conserve precious resources. The stakes are high. Every kilogram of fuel saved means more space for scientific equipment, life support systems, or even additional crew members. Faster travel times also minimize the risks of radiation exposure and psychological strain on astronauts. Beyond the practical benefits, advanced propulsion systems could unlock unprecedented opportunities for exploration. Imagine reaching distant worlds in a fraction of the time, or launching missions that were once thought impossible. The economic and scientific rewards would be immense, opening new frontiers for discovery and innovation. That's where the next generation of propulsion technologies comes in, systems designed to push the boundaries of what's possible in space travel. From ion drives to nuclear thermal propulsion, these innovations promise to address the challenges we face and take us further than ever before. The foundation of space travel as we know it rests on a technology that's both familiar and remarkable: chemical propulsion. For decades, this method has been the driving force behind humanity's greatest achievements in space, from the lunar landings to the deployment of satellites. At its core, chemical propulsion works by burning fuel, like liquid hydrogen or kerosene, with an oxidizer such as liquid oxygen to produce a powerful burst of thrust. This reaction creates the explosive force needed to launch rockets out of Earth's atmosphere and propel them through the vacuum of space. The Saturn V rocket, which carried astronauts to the Moon during the Apollo missions, is perhaps the most iconic example of this technology in action. Standing over 110 meters tall, it generated a staggering 7.6 million pounds of thrust at liftoff, making it one of the most powerful machines ever built. Chemical propulsion's strengths are undeniable. It's reliable, relatively simple to engineer, and capable of delivering the immense power required for launch. But for all its success, this method has significant drawbacks. The biggest issue is its inefficiency. Chemical rockets burn through massive amounts of fuel at an alarming rate, limiting how far and how fast they can go. This makes them less practical for long-distance missions where every kilogram of fuel counts. Additionally, the speed they can achieve is constrained by the energy released during combustion, meaning even the most advanced chemical rockets struggle to reach destinations beyond our solar system in a reasonable time frame. While these limitations haven't stopped us from achieving incredible feats, they highlight the need for propulsion systems that can take us further, faster, and with fewer resources. As we set our sights on more ambitious goals, like crewed missions to Mars and beyond, it's clear that chemical propulsion, while foundational, is just the beginning of our journey into the cosmos. Now, let's shift our focus to a technology that's quietly revolutionizing space travel: electric propulsion. Unlike the fiery bursts of chemical rockets, electric propulsion systems operate on a completely different principle. They use electric fields to accelerate charged particles, typically ions, to generate thrust. This method might sound like science fiction, but it's already being used in space today. Two of the most well-known types are ion thrusters and Hall effect thrusters, both of which have proven their worth in missions where efficiency is key. Here's what makes them stand out. They require far less fuel than chemical rockets, making them ideal for long-duration missions. NASA's Dawn mission, which explored the asteroid Vesta and the dwarf planet Ceres, is a prime example. Powered by an ion thruster, Dawn traveled billions of kilometers over nearly a decade, all while using just a fraction of the fuel a chemical rocket would have needed. The secret to their efficiency lies in the way they operate. Instead of relying on rapid combustion, electric propulsion systems generate a steady, continuous stream of thrust. While this thrust is gentle, often compared to the force of a sheet of paper resting on your hand, it builds up over time, allowing spacecraft to reach impressive speeds. However, this low thrust comes with a trade-off. Electric propulsion isn't well suited for missions that require quick maneuvers or rapid acceleration. For example, it wouldn't be practical for a crewed mission to Mars, where getting there quickly is essential to minimize risks to astronauts. Despite this limitation, electric propulsion has already proven its value in specific applications, particularly for uncrewed probes and satellites. Its ability to conserve fuel and sustain long missions makes it a critical tool for exploring distant corners of our solar system. But as we look to the future, the challenge is clear. How can we combine the efficiency of electric propulsion with the higher thrust levels needed for faster interplanetary travel? That's where hybrid systems and next-generation technologies come into play, offering the promise of the best of both worlds. What if we could harness the immense energy of nuclear reactions to propel spacecraft farther and faster than ever before? That's the promise of nuclear thermal propulsion, or NTP, a technology that takes the power of the atom and channels it into thrust. Here's how it works. A nuclear reactor heats a propellant, typically hydrogen, to extremely high temperatures. The superheated gas is then expelled through a nozzle, creating thrust. This method offers a significant advantage over chemical rockets. It's far more efficient, allowing spacecraft to travel greater distances at higher speeds with less fuel. Imagine cutting the travel time to Mars from months down to weeks. That's the kind of leap NTP could make possible. The concept isn't new. Back in the 1960s, NASA and the Atomic Energy Commission developed the Nuclear Engine for Rocket Vehicle Application, or NERVA, a groundbreaking project that successfully tested NTP systems. While NERVA was cancelled due to budget cuts and shifting priorities, it proved the feasibility of this technology. Fast forward to today, and NTP is experiencing a resurgence. NASA, along with private companies, is actively working on modernizing this approach for crewed missions to Mars and beyond. But as with any nuclear technology, there are challenges to overcome. Safety is a top concern. How do we ensure the reactor remains stable during launch and operation? And then there's public perception. The word nuclear often raises eyebrows, and addressing these concerns is crucial for gaining widespread support. Despite these hurdles, the potential benefits are hard to ignore. NTP could revolutionize interplanetary travel, making it faster, more efficient, and more practical. And as we explore even more advanced nuclear-based systems, the possibilities for pushing the boundaries of space exploration become even more exciting. But what if we could combine the best aspects of nuclear and electric propulsion into a single, groundbreaking system? Enter nuclear electric propulsion, or NEP, a technology that merges the efficiency of electric thrusters with the immense energy of nuclear reactors. Here's how it works. A compact nuclear reactor generates electricity, which is then used to power electric propulsion systems like ion or Hall effect thrusters. This hybrid approach offers a unique advantage. It provides a continuous, high-efficiency thrust over long periods, making it ideal for missions that require both speed and endurance. Picture a spacecraft powered by NEP. It could travel to the outer planets like Saturn or Neptune in a fraction of the time it would take with traditional methods. The system's ability to sustain thrust for years without refueling opens up possibilities for exploring distant, resource-rich regions of the solar system. Theoretical designs for Mars missions have already explored the potential of NEP, suggesting it could reduce travel time significantly while also reducing the need for massive fuel reserves. But the benefits don't stop there. NEP could also support larger, more complex missions, such as transporting habitats or equipment for future colonies. Of course, there are challenges to address, like ensuring the safety and reliability of nuclear reactors in space and managing the heat generated by the reactor. Despite these hurdles, NEP represents a leap forward in propulsion technology, blending proven methods with cutting-edge innovation. And as we continue to push the boundaries of what's possible, even more futuristic concepts are waiting in the wings, ready to take us even further into the cosmos. And now, imagine a spacecraft that doesn't rely on fuel or engines, but instead glides through space powered by the gentle push of sunlight. This isn't a scene from science fiction. It's the reality of solar sails, a propulsion method as elegant as it is innovative. Solar sails work by capturing the momentum of photons, the tiny particles that make up light. When sunlight strikes the sail's reflective surface, it exerts a small but continuous force, gradually accelerating the spacecraft. The beauty of this system lies in its simplicity and sustainability. Unlike traditional propulsion methods, solar sails require no fuel whatsoever, making them an incredibly efficient and cost-effective option for certain types of missions. One of the most notable demonstrations of this technology came from Japan's Ikaro's mission in 2010. As the first spacecraft to successfully use a solar sail for propulsion, Ikaro's proved the concept's viability, traveling through the solar system powered solely by sunlight. But while solar sails offer a promising solution for exploration, they do have limitations. Their thrust is extremely low, meaning acceleration is slow and steady rather than rapid. Additionally, their effectiveness diminishes as they move farther from the sun, since sunlight becomes weaker with distance. This makes them less suitable for missions to the outer planets or interstellar travel. Despite these challenges, solar sails remain a compelling option for specific applications, such as monitoring the sun or studying near-Earth asteroids. And as researchers explore ways to enhance their capabilities, such as combining them with lightweight lasers or advanced materials, the potential for this technology continues to grow. Or what if we could propel a spacecraft to Mars in mere weeks, not with traditional rockets, but with beams of light? That's the bold vision behind laser propulsion, a concept that could redefine the speed limits of space travel. This technology works by using powerful lasers, either ground-based or stationed in space, to direct beams of energy at a spacecraft equipped with a reflective sail. The photons in the laser beam transfer their momentum to the sail, pushing the spacecraft forward. The result, accelerations unlike anything we've seen before, potentially reaching speeds that could slash the travel time to Mars from months to weeks or even days. But the ambitions don't stop there. Take the Breakthrough Starshot initiative, for example, which aims to send tiny, wafer-sized probes to Alpha Centauri, our nearest star system, using laser propulsion. These probes, traveling at a staggering 20% the speed of light, could reach Alpha Centauri in just 20 years, a journey that would take tens of thousands of years with current technology. It's a concept that feels straight out of science fiction, but the science behind it is very real. However, there are significant hurdles to overcome. Building lasers powerful enough to propel a spacecraft requires immense energy, and controlling the beam's precision over vast distances presents its own set of challenges. Then there's the spacecraft itself. How do we design a lightweight sail that can withstand the intense heat and pressure of a laser beam without disintegrating? Despite these obstacles, laser propulsion offers a tantalizing glimpse into a future where interstellar travel could become a reality. And while it's just one piece of the puzzle, it's a reminder that the next great leap in propulsion might come from ideas that seem impossible until they're not. What powers the stars? The answer lies in fusion, the process of combining lighter atomic nuclei to form heavier ones, releasing vast amounts of energy in the process. This same phenomenon could one day propel spacecraft to the farthest reaches of the galaxy. Fusion propulsion, as it's called, replicates the reactions that occur in stars like our Sun, offering the potential for unprecedented energy and speed. Imagine a spacecraft that doesn't rely on bulky fuel tanks, but instead uses onboard fusion reactors to generate thrust. The energy density of fusion is staggering millions of times greater than chemical reactions, making it a game changer for interstellar travel. With fusion propulsion, missions to distant star systems could become feasible, reducing travel times from centuries to decades or even years. One exciting project in this field is NASA's Direct Fusion Drive, or DFD, which aims to develop compact fusion reactors for spacecraft. If successful, it could revolutionize everything from interplanetary travel to energy generation in space. But despite its promise, fusion propulsion faces significant challenges. Sustaining a controlled fusion reaction, a process that requires extremely high temperatures and pressures, remains a monumental task. Scientists have yet to achieve a net energy gain in terrestrial fusion reactors, let alone miniaturize the technology for spacecraft. Stability, efficiency, and safety are all critical hurdles that must be overcome. Still, the potential rewards are too great to ignore. Fusion propulsion could unlock the ability to explore neighboring star systems, study exoplanets up close, and even search for signs of extraterrestrial life. It's a technology that bridges the gap between science fiction and reality, offering a glimpse into a future where the stars are within our reach. Now, let's dive into what could very well be the ultimate energy source for space travel: antimatter propulsion. At first glance, it sounds like something straight out of a science fiction novel, but antimatter is very real, and it's one of the most energy-dense substances known to science. Here's how it works. When antimatter comes into contact with matter, they annihilate each other, converting their entire mass into energy. This process releases an astonishing amount of power, far more than nuclear fission or fusion. In fact, just 1 gram of antimatter could produce the energy equivalent of a small nuclear bomb. Imagine harnessing that kind of energy to propel a spacecraft. Theoretically, antimatter propulsion could enable near-light-speed travel, turning journeys that currently take decades into trips of just a few years. It's a concept that could unlock the stars, making interstellar exploration not just possible but practical. Scientists have already explored designs for antimatter engines, such as the positron dynamics concept, which uses positrons, the antimatter counterpart to electrons, to generate thrust. These engines wouldn't require massive fuel tanks, allowing spacecraft to be lighter, faster, and more efficient. But here's the catch: antimatter is notoriously difficult to produce and store. Currently, we can only create tiny amounts in particle accelerators, and its incredibly expensive estimates suggest it would cost tens of billions of dollars to produce a single gram. Storing it is another challenge, as antimatter must be kept in highly specialized magnetic fields to prevent it from coming into contact with matter and annihilating prematurely. Despite these hurdles, the potential of antimatter propulsion is simply too tantalizing to ignore. It represents the cutting edge of propulsion technology, pushing the boundaries of physics and engineering. And as we continue to explore new ways to produce and harness antimatter, the dream of traveling to distant stars may one day become a reality. Now, let's step into the realm of theoretical physics with one of the most captivating ideas in space travel: warp drives. At its core, a warp drive doesn't propel a spacecraft through space, it bends space itself. Picture this: instead of traveling vast distances, the spacecraft contracts the space in front of it and expands the space behind, effectively creating a warp bubble. Inside this bubble, the ship remains stationary while the fabric of spacetime moves around it. This concept, rooted in Einstein's theory of general relativity, suggests that faster-than-light travel could be possible without breaking the laws of physics. The most well-known model for this is the Alcubierre drive, proposed by physicist Miguel Alcubierre in 1994. His theory posits that by manipulating spacetime in this way, a spacecraft could theoretically reach distant stars in a fraction of the time it would take with conventional methods. But here's the catch: the energy required to create such a warp bubble is mind-boggling. Early estimates suggested it would take the equivalent of mass energy of an entire planet like Jupiter to power the drive. More recent studies have refined this figure, but the requirements remain astronomically high. Beyond the energy challenge, there are other hurdles, like generating and stabilizing the exotic matter needed to bend spacetime in the first place. And then there's the question of practicality. How do we even begin to build something like this? While warp drives remain firmly in the realm of speculation for now, their potential is undeniable. Imagine reaching Alpha Centauri, our nearest star system, in just a few years rather than millennia. It's a dream that pushes the boundaries of science and challenges our understanding of the universe. But as we ponder these far-off possibilities, it's worth remembering that the future of space travel will also rely on more immediate, achievable technologies. These near-term solutions may not take us to the stars, but they'll pave the way for the breakthroughs that could one day make interstellar exploration a reality. Now, let's turn our attention to a technology that sparked both excitement and skepticism in equal measure: the EmDrive, or electromagnetic drive. At its core, the EmDrive claims to achieve something that seems to defy the laws of physics. It generates thrust without the need for propellant. Here's how it supposedly works. Microwaves bounce around inside a conical chamber, creating a pressure imbalance that produces thrust. If true, this would be a monumental breakthrough, effectively eliminating the need for fuel and opening up entirely new possibilities for space travel. But here's where things get tricky. The EmDrive operates in a legal gray area when it comes to Newton's third law of motion, which states that for every action there's an equal and opposite reaction. Without expelling mass, the drive appears to violate this fundamental principle, leading many scientists to question its validity. Despite these concerns, the idea has been too intriguing to ignore. Organizations like NASA and independent researchers have conducted experiments to test the EmDrive's claims. Some tests have reported small but measurable thrust, while others have dismissed the results as experimental errors or external influences like thermal effects. The inconclusive nature of these findings has only deepened the controversy. Proponents argue that the EmDrive could revolutionize space travel, offering a lightweight, fuel-free propulsion system that could make long-distance missions more practical. Critics, on the other hand, remain unconvinced, pointing to the lack of a clear scientific explanation and the potential for measurement errors. So, where does this leave us? The EmDrive remains a tantalizing possibility, one that could either redefine our understanding of physics or fade into obscurity as a fascinating but unproven concept. It's a reminder that innovation often walks a fine line between groundbreaking discovery and wishful thinking. Taking a step back, let's consider the bigger picture. From chemical rockets to fusion drives, and from solar sails to the enigmatic EmDrive, each propulsion system offers unique advantages and challenges. Chemical rockets, while powerful and reliable, are limited by their inefficiency and fuel requirements. Electric propulsion brings incredible efficiency but struggles with low thrust. Nuclear propulsion promises higher speeds and greater range, yet faces technical and safety hurdles. Solar sails offer a fuel-free solution, but their effectiveness diminishes with distance from the sun. And the EmDrive, while controversial, represents a bold attempt to rethink propulsion entirely. Each of these technologies has its place in the evolving narrative of space exploration. Some are proven and practical, while others remain aspirational, pushing the boundaries of what we think is possible. Together, they form a mosaic of innovation, each contributing to the ultimate goal of making space travel faster, safer, and more accessible. As we continue to explore these possibilities, one thing is clear: the future of propulsion is as diverse as it is exciting, and the journey to uncover its full potential is just beginning. Now that we've explored the incredible diversity of propulsion systems, let's take a moment to compare their strengths and limitations. Think of it as weighing the options for a cosmic road trip. Each method offers a unique balance of speed, efficiency, and practicality. Starting with our trusty workhorse, chemical propulsion, we see undeniable power for launches but limited efficiency for long journeys. It's like a gas-guzzling muscle car, great for short bursts but not ideal for cross-country treks. On the other end of the spectrum, electric propulsion excels in fuel efficiency, making it a perfect choice for uncrewed probes or satellites. However, its low thrust makes it less suitable for missions requiring quick maneuvers or rapid acceleration. Nuclear propulsion, both thermal and electric, bridges the gap, offering higher speeds and greater range without the fuel constraints of chemical rockets. It's like upgrading to a hybrid vehicle, more efficient and capable of handling longer trips. Solar sails, while elegant and fuel-free, are best suited for missions close to the sun where sunlight is abundant. And then there's the EmDrive, a wild card that, if proven viable, could redefine propulsion altogether. Each system has its niche, from near-term missions to Mars to the far-off dream of interstellar travel. But what makes one technology more feasible than another? Factors like development cost, safety, and public acceptance play a huge role. Systems like electric propulsion and nuclear thermal propulsion are already being tested and refined, making them strong candidates for near-future missions. Others, like fusion drives or antimatter propulsion, remain in the realm of theoretical research but hold immense promise for the decades ahead. As we weigh these options, it's clear that the future of space travel will rely on a mix of proven technologies and bold innovations. Each step forward brings us closer to unlocking the full potential of propulsion and the stars beyond. While the potential of these advanced propulsion systems is undeniably exciting, developing them isn't without its hurdles. Imagine trying to build a car that can drive to the moon, except the road doesn't exist yet, and you're inventing the engine as you go. That's the kind of challenge engineers and scientists face when pushing the boundaries of propulsion technology. One of the biggest obstacles is funding. Projects like nuclear thermal propulsion or antimatter drives require billions of dollars and decades of research. Even smaller-scale initiatives like electric propulsion systems demand significant investment in testing and development, and with space agencies and private companies often operating on tight budgets, securing the necessary resources can be a constant struggle. Take the case of NASA's Prometheus project in the early 2000s, which aimed to develop nuclear-powered spacecraft. Despite its promise, the program was cancelled due to budget constraints, a reminder of how financial realities can derail even the most ambitious plans. Safety is another major concern, especially when dealing with technologies like nuclear or antimatter propulsion. How do we ensure these systems won't malfunction in space or pose risks during launch? Public perception adds another layer of complexity. Technologies involving nuclear reactions or untested physics can spark fear and skepticism, making it harder to gain public and political support. Ethical considerations also come into play, particularly when discussing the environmental impact of testing or the potential militarization of space technologies. Despite these challenges, history shows that collaboration and innovation can lead to breakthroughs. Take the International Space Station, for example, a project that brought together multiple nations and disciplines to achieve what seemed impossible. Similarly, partnerships between governments, private companies, and academic institutions are key to overcoming the hurdles in propulsion development. By sharing knowledge, pooling resources, and fostering creative problem-solving, we can turn these challenges into stepping stones toward a brighter future in space exploration. And now, let's shift our focus to the dynamic world of private space companies, where innovation is happening at an unprecedented pace. Over the past 2 decades, companies like SpaceX, Blue Origin, and Rocket Lab have transformed the space industry, bringing fresh ideas and a competitive edge to propulsion technology. At the forefront of this movement is SpaceX, which has revolutionized space travel with its reusable Falcon rockets. By recovering and reusing boosters that would traditionally be discarded after a single launch, SpaceX has dramatically reduced the cost of reaching orbit. This breakthrough isn't just about saving money, it's about making space more accessible for a wider range of missions, from satellite deployments to crewed flights. Blue Origin, founded by Jeff Bezos, has also made significant strides with its new Shepard rocket, designed for suborbital space tourism, and its upcoming New Glenn rocket, which aims to compete with SpaceX's heavy lift capabilities. Meanwhile, smaller players like Rocket Lab are making waves with their Electron rocket, which specializes in launching small satellites into orbit quickly and affordably. These companies aren't just building rockets, they're rethinking the entire approach to space travel, from propulsion systems to manufacturing techniques. One of the key drivers behind this innovation is competition. With multiple players vying for contracts and market share, the pace of development has accelerated dramatically. Private investment has also played a crucial role, providing the resources needed to take risks and explore bold new ideas. But it's not just about the private sector. Government agencies like NASA and ESA have been instrumental in fostering this ecosystem, offering contracts, partnerships, and support for emerging technologies. Together, this collaboration between public and private entities is pushing the boundaries of what's possible in propulsion, paving the way for a future where space travel is faster, cheaper, and more accessible than ever before. While private companies are driving innovation, government agencies remain at the heart of space exploration, shaping the future of propulsion technologies through ambitious projects and international collaboration. NASA, for instance, has been a pioneer in this field for decades, from developing the iconic space shuttle to its ongoing work on nuclear thermal propulsion. The agency's Artemis program, which aims to return humans to the moon by 2025, is a prime example of how cutting-edge propulsion systems are being integrated into modern missions. Artemis isn't just about reaching the moon, it's about establishing a sustainable presence there, using advanced propulsion technologies to enable longer stays and more complex operations. And NASA isn't doing it alone. The European Space Agency, or ESA, is a key partner in Artemis, contributing expertise and resources to develop the Lunar Gateway, a space station that will orbit the moon and serve as a hub for exploration. This spirit of collaboration extends beyond individual programs. Agencies from countries like Japan, Canada, and the United Arab Emirates are also involved, proving that space exploration is increasingly a global effort. These partnerships aren't just about sharing the workload, they're about pooling knowledge, expertise, and resources to tackle challenges that no single nation or organization could solve alone. Take the International Space Station, for example, a joint project involving 15 nations. It has become a symbol of what humanity can achieve when we work together. The same collaborative spirit is now being applied to propulsion research, with agencies sharing data, conducting joint experiments, and co-developing technologies. But what does the future hold for these partnerships as missions grow more ambitious? From crewed missions to Mars to the development of interstellar probes, the need for international cooperation will only increase. By combining our strengths and resources, we can accelerate progress, reduce costs, and ensure that the benefits of space exploration are shared by all. While the spotlight often shines on industry giants like SpaceX and Blue Origin, there's a growing wave of startups making waves in the world of propulsion. These smaller, nimble companies are bringing fresh perspectives and bold ideas to the table, challenging the status quo and pushing the boundaries of what's possible. Take Momentous, for example. This California-based startup is developing in-space propulsion systems that use water plasma as fuel, a concept that's both innovative and sustainable. Their technology could revolutionize how satellites maneuver in orbit, offering a cost-effective and environmentally friendly alternative to traditional methods. Then there's Rocket Lab, a company that's become a major player in the small satellite market. Their Electron rocket, powered by electric pump-fed engines, has already launched dozens of missions, demonstrating that smaller, more frequent launches can be just as impactful as larger ones. What sets these startups apart is their ability to take risks and experiment with unconventional ideas. Without the bureaucracy of larger organizations, they can move faster, iterate quickly, and adapt to new challenges. But innovation doesn't come without hurdles. Competing with established giants is no small feat, especially when it comes to securing funding, attracting talent, and gaining customer trust. Many startups also face technical challenges, from scaling up their designs to ensuring reliability in the harsh environment of space. Despite these obstacles, their contributions are invaluable, driving progress and inspiring the industry as a whole. As we look ahead, the next decade promises to be a transformative period for propulsion development. Established players will continue to refine their technologies, while startups will push the envelope with disruptive ideas. Together, this ecosystem of innovation could lead to breakthroughs we can hardly imagine today, whether it's faster interplanetary travel, more efficient satellite systems, or entirely new ways to explore the cosmos. Looking ahead to the next 10 years, the advancements in propulsion technology could redefine our relationship with space. By the mid-2020s, we're likely to see the first operational nuclear thermal propulsion systems, paving the way for faster and more efficient missions to Mars. These systems, which use nuclear reactors to heat propellants, could cut travel times significantly, making crewed missions to the Red Planet more feasible. Around the same time, electric propulsion is expected to take a leap forward, with next-generation ion and Hall effect thrusters offering higher thrust levels and greater efficiency. These improvements could make electric propulsion a viable option for crewed missions, opening up new possibilities for interplanetary travel. By the end of the decade, we might also witness the first successful tests of fusion propulsion systems, a technology that could eventually enable interstellar exploration. Projects like NASA's direct fusion drive are already making strides, and while the challenges are immense, the potential rewards are equally staggering. Improved solar sail technology could also come into play, offering a fuel-free solution for long-duration missions within our solar system. These advancements won't just make space travel faster, they'll make it more sustainable, reducing our reliance on finite resources and minimizing the environmental impact of exploration. The ripple effects of these breakthroughs will be profound. Faster, more efficient propulsion systems could accelerate plans for lunar and Martian colonies, making it easier to transport people, equipment, and supplies. They could also expand our ability to explore the outer planets, providing new insights into worlds like Europa and Enceladus, which are thought to harbor potential for life. And of course, they'll bring us closer to the ultimate goal, interstellar travel. While the next decade will undoubtedly bring challenges technological, financial, and ethical, it also promises to be a period of unprecedented progress. The milestones we achieve in this time won't just shape the future of space exploration, they'll inspire generations to dream bigger and reach further into the cosmos. Interstellar travel has long been the stuff of dreams, a vision of humanity reaching beyond our solar system to explore distant stars. But could this dream actually become a reality? The answer lies at the intersection of ambition and innovation. The first hurdle is the sheer scale of the challenge. The nearest star system to Earth, Alpha Centauri, is about 4.37 light-years away. That's roughly 41 trillion kilometers, a distance so vast that even with our fastest current propulsion systems, it would take tens of thousands of years to reach it. For perspective, Voyager 1, the farthest human-made object from Earth, has been traveling since 1977 and has only just entered interstellar space. At its current speed, it would take over 70,000 years to reach Alpha Centauri. Clearly, we need something far more advanced than chemical rockets or even nuclear propulsion to make interstellar travel feasible. That's where emerging technologies come into play. Concepts like antimatter propulsion, fusion drives, and even laser-powered light sails offer potential solutions. Breakthrough Starshot, for instance, envisions sending tiny, lightweight probes to Alpha Centauri at 20% the speed of light, completing the journey in just 20 years. While this is a far cry from crewed missions, it's a tangible step toward proving that interstellar travel is possible. But speed isn't the only challenge. Sustaining human life on such journeys is another monumental task. Issues like radiation exposure, psychological strain, and the need for self-sustaining ecosystems must be addressed. Even with advanced propulsion, a crewed mission to Alpha Centauri would require a spacecraft capable of supporting life for decades or even centuries. Despite these obstacles, the progress we're making is undeniably exciting. While interstellar travel may not happen in our lifetimes, the groundwork being laid today, through research, experiments, and international collaboration, could set the stage for breakthroughs in the next century. The implications of such advancements extend far beyond exploration. Mastering interstellar travel would not only expand our understanding of the universe, but also open up new opportunities for resource utilization, scientific discovery, and even the survival of humanity. It's a vision that challenges us to think bigger, work harder, and dream without limits. The advancements in propulsion technology we've been exploring aren't just about getting to Mars or reaching the stars, they're about reshaping humanity's future in profound and far-reaching ways. Imagine a world where faster space travel enables us to establish colonies on the Moon, Mars, and beyond, creating self-sustaining habitats that could one day serve as a second home for our species. This isn't just science fiction, it's a tangible possibility within our lifetimes. By reducing travel time and improving efficiency, advanced propulsion systems could make space colonization more practical, opening up new frontiers for exploration and settlement. But the benefits extend far beyond colonization. Picture the economic potential of mining asteroids for rare metals or harnessing solar energy in space. These resources could revolutionize industries on Earth, providing materials for everything from renewable energy technologies to advanced electronics. The scientific discoveries alone could transform our understanding of the universe, from uncovering the secrets of distant planets to potentially finding signs of extraterrestrial life. Each step forward in propulsion technology brings us closer to these possibilities, turning what once seemed like fantasy into achievable goals. Beyond the practical benefits, there's something even more inspiring at play. The pursuit of advanced propulsion systems has the power to unite humanity in a shared vision of exploration and discovery. It's a reminder that, despite our differences, we're all part of the same journey, one that extends beyond our planet and into the cosmos. This shared ambition could foster international collaboration, bringing people together to solve challenges that no single nation could tackle alone. And perhaps most importantly, it has the potential to ignite the imaginations of future generations, inspiring them to dream big and pursue careers in science, engineering, and exploration. Initiatives like NASA's Artemis program and private ventures like SpaceX are already capturing the public's imagination, showing what's possible when we invest in bold ideas. But as we look to the future, it's essential to also consider the ethical implications of these advancements. How do we ensure that space exploration benefits all of humanity, not just a select few? What safeguards are needed to protect celestial environments from exploitation or contamination? These questions remind us that with great power comes great responsibility. The choices we make today will shape the trajectory of space exploration for centuries to come, and it's up to us to ensure that this future is both equitable and sustainable. As we push the boundaries of propulsion technology, it's crucial to pause and consider the ethical implications that come with such advancements. Think about it. As we develop systems capable of taking us to distant worlds, we're also creating technologies that could have far-reaching consequences for both Earth and space itself. One of the most pressing concerns is the environmental impact. Traditional chemical rockets, for example, release significant amounts of pollutants into the atmosphere during launch. While newer systems like electric propulsion are cleaner, the production and testing of advanced technologies, especially those involving nuclear materials, raise questions about sustainability and long-term effects on our planet. Then there's the issue of safety. Systems like nuclear, thermal, or fusion propulsion, while incredibly powerful, come with inherent risks. How do we ensure these technologies won't fail catastrophically, endangering astronauts or even populations on Earth? The development of antimatter propulsion adds another layer of complexity, as the production and storage of antimatter pose unique challenges that must be addressed with rigorous safety protocols. Beyond these technical concerns, there's a broader ethical question. How do we prevent the militarization of space? History has shown that technological advancements often have dual uses, with applications in both exploration and warfare. The same propulsion systems that could take us to Mars or beyond could also be weaponized, potentially sparking a new arms race in space. This underscores the urgent need for international regulations and agreements to ensure that space remains a domain for peaceful exploration and scientific discovery. Balancing innovation with ethical responsibility isn't just a challenge, it's a necessity. We must approach these advancements with a sense of stewardship, ensuring that our pursuit of progress doesn't come at the expense of safety, equity, or the environment. This is where collaboration becomes key. By fostering partnerships between governments, private companies, and international organizations, we can create frameworks that promote responsible innovation while addressing the complex ethical dilemmas that arise. It's a delicate balance, but one that's essential for the long-term success of space exploration. At the same time, we can't lose sight of the transformative potential of these technologies. From enabling faster interplanetary travel to opening up new frontiers for scientific discovery, advanced propulsion systems offer opportunities that could reshape our future in profound ways. The key lies in navigating these possibilities thoughtfully, ensuring that our journey into the cosmos is not just groundbreaking, but also grounded in ethical principles that benefit all of humanity. As we've journeyed through the possibilities of advanced propulsion systems, one thing is clear: the future of space travel is on the cusp of a revolution. From the tried and true power of chemical rockets to the futuristic promise of antimatter drives, each technology offers a unique piece of the puzzle. Electric propulsion has already proven its worth for unmanned missions, demonstrating that efficiency can take us far, even if the journey is gradual. Nuclear propulsion, with its ability to shrink travel times to Mars, offers a tangible step toward crewed interplanetary exploration. And then there's the speculative yet thrilling realm of warp drives and antimatter engines, technologies that could one day make interstellar travel a reality. These advancements aren't just about going faster or farther, they're about transforming how we see ourselves in the universe. Space travel has always been a testament to human ingenuity and curiosity, and with each leap in propulsion technology, we're reminded that there's still so much to discover and achieve. The potential is staggering. Faster travel could open up new opportunities for scientific research, resource utilization, and even the colonization of other worlds. It could redefine our understanding of where humanity belongs, shifting our perspective from Earth-bound beings to explorers of the cosmos. But perhaps the most exciting aspect is the unknown. Every breakthrough in propulsion brings us closer to answering questions we haven't even thought to ask yet. What might we find on distant planets? Could we one day encounter extraterrestrial life? These questions remind us that the universe is full of possibilities, and propulsion technology is the key to unlocking them. So, where does this leave us? For now, we're standing at the threshold of a new era in space exploration, one where the stars are not the limit, they are the destination. As we continue to push the boundaries of what's possible, let's remember that the journey is just as important as the destination. What do you think the future of propulsion will bring? Share your thoughts in the comments below. And if you enjoyed this deep dive into the future of space travel, don't forget to subscribe for more insights into the cutting-edge technologies shaping our world. Together, let's keep looking up and dreaming bigger.